Hello all, hope you're doing well. So we are going to discuss about different kind of concentrations and how to calculate the same. So now concentrations, what we know, we are not only discussing about the mass by mass percentage that we can discuss later on. That's only based on solute and solution amount. So what we are discussing over here is how much amount of solute that you add in total solution and how you can relate with the number of moles. So we have concentration where you calculate on the basis of amount of solute and the amount of solution where number of moles you're not going to consider. Those are different concentrations, mass by mass, mass by volume and volume by volume percentage that I'll be dealing with the separate video. But over here in today's class, we are going to discuss about concentrations where number of moles play an important role. So we are going to start with the very first concentration, that is molarity. We denote with the help of capital M. So I'll be defining first molality, mole fraction. Three I'm going to define, then we'll do a collective numerical just to understand it better. So what is molarity? It's a concentration, right? So molarity is defined as number of moles of solute per liter volume of solution. So according to definition, the volume of solution has to be in liters. So number of moles, you already know what's the unit of number of moles. You can check those videos on my channel. So according to this definition, we can say molarity is like units of molarity if you want to write. This is mole per liter according to, you can say, the formula. You can write in the definition part, like in the statement form also, number of moles of solute per liter volume of solution. So now let's try to understand molarity is equal to number of moles of solute divided by volume of solution, that is in liters, correct? Now what do we understand with this formula? That molarity is inversely proportional to volume and molarity is directly proportional to number of moles of what? Solute. Now if we want to open this particular formula, so number of moles is given weight, or you can say given mass also, you can say. So I'll write it in the form of given mass divided by molar mass. So molar mass can be, you can say, a gram atomic mass over here. Like you can consider gram atomic mass, you can consider this gram molecular mass depending upon what they have given in the question. So obviously we are talking about molarity. Molarity needs to be for particular compounds. We are not talking about single elements over here. So then this is number of moles. So if we open it, divide it by again volume of solution. It's not for solvent, it's solution, and if it is given in ml, you divide this volume by 1000. So I'm basically, you divide this volume divided by 1000. So this is how you're going to write into 1000 this entire thing. So this, you can say, is number of moles of solute divided by volume of solution into 1000. So you can open the structure, or not structure, sorry. You can open the formula like this also. So now molarity, if you can see, since it's dependent upon volume, so molarity is temperature dependent. So what do you understand by this? How we can prove that it is temperature dependent? So you go back to the basics part. Basics in the sense, we are talking about liquids, no doubt. What concept we are picking up actually is used in the gaseous state. So we know that volume is directly proportional to temperature. This is something taught in gaseous state Charles law, that again we can discuss later on, but not right now. So meaning, if you talk about any kind of, you can say, you have volume, we are applying to the liquid, right? But this is actually applied in the gases, but we can apply over here in the liquid also. So let's say if you have a beaker and if you have water in it, right, and you are heating it, with a Bunsen flame, right? So this is just simple hypothetical diagram I'm drawing over here. But try to understand that if you have water over here and if you're heating it, so don't you think the water will start forming vapors over here, and it is going to occupy this entire beaker, and ultimately they will be released into the atmosphere. So meaning over here that if you increase the temperature, volume will be impacted. So increase in volume, decrease in volume can happen with the impact of temperature over here. So if volume is dependent upon temperature, then why can't we say molarity is temperature dependent? So it is temperature dependent. Wherever you will have this volume factor anywhere considered in any concentration, temperature will be impacted. Like you can say temperature can be modified and volume can also be modified. Ultimately it is going to affect the concentration term over there. So ultimately molarity is going to be impacted. Now, if you remember, this part I haven't dealt right now, but we'll be dealing it about it soon. Temperature is directly proportional to kinetic energy of the particles. This is like very general. You can say if we try to increase the temperature of any particular substance, whether it's gas, whether it's liquid, so kinetic energy of the particles will be increasing for sure, because they are directly related, because they are all energy. It's a type of energy. So if you're giving heat, so energy is absorbed by the particles, so obviously kinetic energy will increase if you increase the temperature, and same apply for decreasing the temperature also. So molarity is very much temperature dependent, so we need to remember that. Then we come to the second concentration, that is molality. Molality is obviously, if you see the term, there is only difference between L and R, but actually there's a lot of other differences also. Molality is given by small m, it's not capital M. So it's given by the same number of moles of solute. I'm writing the whole sentence right now, but otherwise you can shorten it up, just write number of moles of solute divided by weight of solvent, that has to be in kgs. So according to definition, you need to remember molarity is volume of solution in liters always, right? And one more thing I messed up, not messed up, it's I missed. So we can actually write capital M molar for this units, or just simple M. So this is a unit of like 3m. If I'm writing that, states it's 3 is a molarity of particular solution over here. So molality, if we say number of moles of solute divided by weight of solvent in kgs, so it's never going to be volume of solution, so it's solvent that we're considering. So you can even write like this: weight of solvent, that is in kg. Now if you want to open the number of moles of solute, given mass divided by molar mass, then divided by weight of solvent. Weight of solvent, if it is in grams, again divided by 1000. So we need to remember. Now we can see one more thing over here, there is no volume factor considered. So if volume factor is not considered, that means molality is temperature independent, right? So because you can even write this, volume factor is not considered in the formula. Obviously the definition is different, right? So this was second concentration. The third concentration that we are going to discuss is mole fraction. Then we'll do a collective numerical. So what is mole fraction? From the term fraction itself, it's a fraction of number of moles, right? So mole fraction, we can calculate for anything. Like there has to be, you can say, a particular solute and there has to be particular solvent. So since we are talking about solutions only, so let's say mole fraction, it's given by this symbol. Most of the books write it in the form of x, but otherwise it's a Greek symbol. It actually stands for chi, chi. This, it's a Greek letter. Again, chemistry people love Greek and Latin, right? So mole fraction of solute, if we are calculating, that will be equal to number of moles of solute. Now, most of the time in the question, they don't give you number of moles directly. Sometimes they do, but most of the time they give you weights. So what do you need to do? You need to check you need to keep the weight divided by its molar mass, right? And then you get the number of moles. But most of the time, what students do this mistake, they directly put, you can say, the given weight over here, and end up having the wrong answer. So because kids are, or you can say all these teenagers are very much, they want fast things, right? So patiently, if you can read a question, give few seconds, give it a thought, half of your problem is solved over there in that single question only. If you read the question properly, if you don't read it, if you're in a haste, if you're in panic mode, okay, what do, I don't know this question, or maybe you read something, you figure it out in your brain something else, and ultimately what you wrote on the paper is something else. So all these three things are not syncing at all. So you need to patiently read the question. Sometimes it happens with me also when I read the question. If I'm like, if I'm in a hurry, so obviously I read the question, I miss something, so then I'm solving it, right? Something is not clicking correct. So again, if you read the question 2 3 times, your brain works properly if you know the concept, and definitely you end up with the correct answer. So mole fraction of solute is number of moles of solute divided by number of moles of solute plus number of moles of solvent. Now, most of the books write number of moles of solution. That's okay. You can actually write that way also. But sometimes in the question, they give you solute weight different, solvent weight different, and sometimes they don't even give you solvent weight, and you have to figure it out yourself. Like for specifically for water, they don't give, and you have to calculate the you can say moles, or like they do give, like we just have to figure it out. We'll do some numericals, then you'll understand. Then we come to the next part, mole fraction of solvent. So point over here is that whatever mole fraction you're calculating for solute or solvent, you keep the number of moles of the same in the numerator over here. So number of moles of solvent divided by same number of moles of solute plus number of moles of solvent. So remember one thing, mole fraction of solute plus mole fraction of solvent, it's a very small value. This is always equal to unity. You have to remember this. So if I have calculated, mole fraction of solute, right, or solvent, so 1 minus mole fraction of solvent, you will get the other mole fraction. You don't need to separately do these two steps. Like one step you have done, subtracted from one, you will get the other value also. Then we even say mole fraction is a dimensionless quantity. It has no units. So mole fraction is a dimensionless quantity. It has no units. So if you see the number of moles of solute and the number of moles of the solvent, if you take over here, both are moles only, right? If you remember from the previous videos, units of number of moles is equal to mol. If you remember, if you have seen those videos, you'll be able to understand it better. Then we can even say mole fraction is independent of temperature, because we don't have any volume factor considered over here. Right, now we go to the numerical. So let's take this example. 5 gram of NaCl is dissolved in 1000 gram of water, right? And one more thing we need to understand is the density of relationship, like relationship of density and molarity. So that also we'll do it. Next part of the question, if the density of the resulting solution is 0.997 gram per cc, cubic centimeter cube. So what do we have to calculate? We have to calculate the molality, we have to calculate molarity, and mole fraction. See, originally in this question, even they have asked normality. I don't want to touch that normality because I want to link that concept with pH. So, anyways, we'll be able to we'll be calculating only these three over here. So now 5 gram of NaCl, that means this is the weight of NaCl given over here, dissolved in 1000 gram of water. So solvent weight they have given, then they have given solute weight. So what do we need to calculate? We need to calculate molarity. So obviously it's molarity of NaCl we need to calculate. We need to calculate molality of NaCl, right? Why do we need water weight over here? Because we need to calculate molality, and according to molality definition, weight of solvent is required. So you need to convert this 1000 gram into kilograms. And for mole fraction, we just need number of moles of water and number of moles of NaCl. So now let's try to solve this. So moles of NaCl if we need to calculate. So given weight is 5 gram, and NaCl, if you already remember it pretty well, if you don't then you can calculate. So sodium chloride, sodium mass is 23 and chlorine is 35.5. So if you add it up, you will get 58.5, right? So this is gram molecular mass, I'm taking grams only. So 5 grams divided by, so let's give the units, divided by 58.5. So this, if you calculate, this will be 0.085. So up to 3 decimals or 2 decimals you can take. Then now if we talk about the very first that we are going to calculate is molality. So molality is moles of NaCl divided by weight of solvent. Over here they are giving you in grams, then do not forget to divide with 1000. So moles we have already calculated, 0.085 we have taken. If you divide it with the weight of solvent, that is 1000, and into 1000, so ultimately you will get the same value, 0.085. Okay, I skipped this part, mole per kg. Now these are the units. Again, I'm going back for a moment. So over here, molality. So units of molality you write. That is mole per kg. We even write like this, molal. And even they sometimes write small m. So if I'm writing 3s with a small m, that indicates its molality. Then if we go to this, so molality we calculated, so at least one part we figured it out, right? Now next part for calculating volume of solution. See, molarity, if you go back over here, molarity we require volume of solution, this part, right? We don't have volume of solution, we have weight of solvent, correct? So how we can do that? We can actually take the help of density, because we know density is also given. So density is equal to mass by volume. This is the formula, right? So if we need to calculate volume, so this will be mass by density, right? So this is nothing but mass of solution. You have to remember one thing, density is always for the solution. It is never for solvent or solute separately, right? Then because we are calculating volume of solution, because we require volume of solution for the molarity, we don't require volume of solute or solvent. So what is mass of solution over here? So this will be equal to mass of solute plus mass of solvent, that we know both of them. 5 gram is a mass of solute and 1000 gram is the mass of solvent. So 1005 gram, 1005 gram will be the mass of solution, divided by density, which is given over here. So 0.997 gram per cc. Right? So now if you see, if we try to divide this value, we will get the volume of solution. So this will be approximately 1008 ml, or we can take it as 1.008 liters. Right, now again we go to the molarity part. Since we have figured out the volume of solution, so it will be moles of NaCl. This also we have calculated. So volume of solution in liters. So moles 0.085 that we had taken over here. Here 0.085. So volume of solution 1.008 liters. So when you divide, you will get this value 0.085. See, this is approximately 1, right? You can skip this part. You can actually get the same value. So this is your molarity, right? Now we go to the mole fraction. So mole fraction we need to calculate for NaCl. So moles of NaCl divided by moles of NaCl plus moles of water. So now if we need to calculate moles of water, we need to remember one thing. So moles of water, if we need to calculate, we know 1000 gram is actually given, right? Divided by 18. 18 is the gram molecular mass of water, right? So when you take this, so this will give you 55.55 moles. This is very famous. You're not famous, I would say, like very commonly used in most of the questions. Now, if we have these, like we can actually take this, we have taken 1000 grams and we are calculating moles. That's okay. We can actually we can even say that for water, like if we say 1 ml is equal to 1 gram for water having density 1 gram per ml, right? So if we need to calculate the total moles now, so this is 55.55 moles plus the moles of NaCl 0.085 moles. So if we add it up, so we will get 55.635. So these moles we got. Now coming back to mole fraction of NaCl, so 0.085 divided by 55.635. So you will get 0.00152, right? This much value if we say. So we can actually shift it, you can say to some decimals we can shift over here, like if we want to. So this can be taken as 1.52 into 10 to the power minus 3, right? So yeah, so this is basically, if you can see over here, so 0.00152. So this is 152 into 10 to the power minus 5 we can take. So 1.52 into 10 to the power minus 3, you can shift the decimal. So that's your answer. So I hope you have understood these three concentrations. I'll be releasing more videos based on pH and normality also, so coming soon, and I'll be starting new chapters soon. So thank you for listening to this video, and I hope if this was helpful, please share it to your friends, to your friends, family, and subscribe my channel. Thank you so much.